Hello everyone, it's September the 25th. Alright, second time. Let's do this. We have satisfiability of equality equations. That looks like a new question. I don't think I've done this before. Maybe I have, I don't know. You're given an array of strings, equations, that represent relationships between variables, where each string, equations I, is of length 4. And takes one of two different forms, either this or this. Here, x and y are lowercase letters, not necessarily different, that represent one-letter variable names, written true if it is possible to assign integers to variable names so as to satisfy all the given equations, or false otherwise. Very interesting. I don't think I've done this before. Okay, so we have about 500 of them, and each one is either equal to or not equal to, so only two possibilities. And the first one is a lowercase letter. It's either this, the second one must be this, it's a lowercase letter. So I think what we can do is just to identify, just go through all of them. I think if it's equal to, we can group them together. Oh, are you saying we use union find? Wait, what are you saying? I don't think it's necessary, right? If A equals to B, I say A will point to B and B will point to A, right? And then if A is not equal to B, then we just, that link just doesn't exist. So how about we do equal first? Yeah, if we do equal first, and then we handle the not equal, then we can see any error immediately, right? So if we do equal first, we actually can use union find. We use union find, we do the equal first. So which one goes first? If I sort them, I don't have to sort them. I think I just separate them, right? If it's equal, hold on. If it's equal, I just union them. And if it's not equal, I save it, right? I save it. So after, but it's only 500, so I can sort. Yeah, I'm gonna sort. All I need to know is which one goes first. Let's say, let's just put this one up. All right, let's say how it goes. If we say this, let's also say C equals D. How about this? All right, and now say full.sort. Oh, I have to go sorted. No, let's go full.sort. No, sorted. I want to test it. Full key equals lambda equation, and I'm going to sort by equation 0, 1. Sort by that. Okay, the exclamation mark goes first. Which is fine. Then we just go from back to front until we hit the first exclamation mark, and then we have a union of everything, and then we go through every one of them just to see if they belong to the same parent. If they don't belong to the same parent, like if they're not equal, that means their parents must not be the same, right? If they're not equal but they belong to the same parent, that means it's not possible. Let's try this idea. I am not ashamed of using union find. I think this is the right way to go. Simple and easy, right? Union find, simple and easy. Okay, the question is, can you write union find? DSU. Let's see. let's see if I can write this. Okay, self.parent is going to list range n, and self.rank equals everybody will rank 0 at the beginning. Okay, so we have def union. Union. We'll say, let's all find first. Find x, right? Return integer. So we say if self.parent x is not equal to x, self.parent x equals self.find x. And then return self.parent x. That's find, right? So like if it's not the same, which means it's not the parent yet, then we'll go find its, and if we have already found, then we call it's actually self.parent x, and the parent, if it's true, then we return parent, and this is path compression. Now, union, we will say union x and y, right? And then we return Boolean value. We say if self.parent x is equal to self.parent y. Now I might actually say px py is equal to this and this, right? We get a parent out and say if px is equal to py, then return false, means we no need to union, already together. Otherwise, they're not the same. Then we say if self.rank px is larger than self.rank py, right? So the parent on x is larger than the parent on y. Then we say self.parent y equals px, right? We assign to px. That's it. If this, let's say it's smaller, then we assign self.parent x equal to py, right? Else, now they're the same, then we arbitrarily say self.parent x, not parent x, rank x, px, right? Px, I say plus equal 1, and then self.parent y equals px. And all this will return true. Okay, so this is my DSU. Now we're gonna go equation.sort lambda. Oh, we actually can reverse. Key equals lambda equation. I think we did it. This is 1. All right, equation 1. So the sort, actually I want to reverse equals true. All right, then we can say for equation and equations, right? Say if equation 1, right, 0, 1 is equal to this, then DSU equals DSU. Lowercase letters, all lowercase letters. So n is going to be 26. I don't have a 26. So that's the case. And DSU.union, right? Equation 0 and equation 3. And else, if it's not, which means these two are different, then we say if DSU.find equation 0 is equal to DSU.find equation 3, then we'll return false. So we can go if this, then return false. It means they're the same. They belong to the same union, right? They belong to the same, but they're saying they're different. So I return false. And at the end, we'll return true if everything goes fine. Okay, so let's see. This one is false, right? And this one is true. we have equations possible. Run it. Ooh. User takes no argument. Huh? Wait, what? No. Wait, hold on. Oh. Ooh. My bad. The ord minus 97, I think. Yep, minus 97, ord minus 97. I could have just do it here. Nah, I want that one to be as generic as possible. Yeah. So the equation says they're different, but they belong to the same group. That will be impossible. Okay. I mean, maybe you can, let's say, B equals C. All right, let's get creative. C equals D, and A not equal to D. Something like this. Okay, let's try it. Yeah, it is a new problem. Oh. A, B, B, C. This is exactly the same thing I was doing. How? Oh. Doesn't make any sense. Okay, let's see. Yeah, you compress, and then this one you compress as well. Unless this was wrong. Let's see. Let's print this one out. Let's see what happens. Huh? It didn't go through this. What? Wait, what the hell? it's not the best way to do this, right? Like after A, B, C, E, B, C, A, and E. Oh my god, my bad. Define Y. Now this is true, we have defined, but that's still not right. BC get to 0, and I find it again. That's interesting. Oh, gotta be something is not right. Let me think. We will union. We find the parent. They're not the same. So I would expect when go A and E, when E, trying to look for its, no, when C, right? Look for they should belong together. Did I do this wrong? Let's see. I think I did it right. Parent, rank, if rank, oh, shoot. Yeah. Parent. My bad, it's the parent. Yeah. Okay, it's not the issue of logic. It's the issue of the DSU. So yeah, it has to be. Yeah, it has to be parent. They go to the parent. We have to change the parent. Yeah, this is pretty bad. It's the parent. There we go. Well, still need practice for union find, right? $990. Not a difficult problem using union find. The most difficult part is still writing DSU from scratch. I almost got it, but I made a mistake. I made a mistake in the union method. So the idea is that we union all the letters that are connected, right, by equal sign first. Then we go through the inequalities. Right, we go through the inequalities. Yeah, we probably need to this. What if you got to ask this question in an interview. You need to ask your table which one comes first. Oh, this is the first one. Exclamation mark is the first one. And quotation mark. Wow, equal sign is late. Okay, equal sign is late. Yeah, I know A is 97, this is 65. I think I know these two. The small a and a big A, one 97, the other 65. I know that. Man, they better allow me to check the ASCII table, otherwise. I mean, there are other ways to do this, but I just feel it's not going to be as effective as this, right? Then I go through the inequalities, and if a pair of letters, right, that are a pair of not equal letters are actually belong, I say, actually belong to the same group, same union, we return false. Union find, the inverse Ackermann function. Oh, I forgot how Ackermann function is, but I just read about it. So I'll say ON, yeah, ON, but this is 26, so we can actually say it's O1 because it's log 26, right? We just call it ON. The union find is alpha 26. Complexity is alpha 26, which is the inverse Ackermann function. And I forgot what Ackermann function is. But anyway, I've read about it, but I forgot. So union find is which is essentially O1. Okay, let's see. Maybe there are methods without using union find. Wow, yeah, it is union find. Yeah. Oh, DFS. Well, you can build a graph. Yes, you build a graph, but then what? Then yeah, I'll multiply the O1 exactly. All right, so that's that. We're done today. Let's try to take a look at this. I don't think I have the gana to do it today, so let's just take a look, see how it looks like. There's a tree, a connected, undirected graph with no cycles, consisting of n nodes numbered from 0 to n minus 1, and exactly n minus 1 edges. Didn't say it's a binary tree. You're given a zero index integer array of vowels of length n, where vowels I denotes the value of the ith node. You're also given a 2D integer array edges where, okay, denotes that there is an indirect edge connecting nodes A and B. Okay, that's fine. A good path is a simple path that satisfies the following conditions. The starting node and the end node have the same value. Okay? All nodes between the starting node and the end node have values less than or equal to the starting node. The starting node's value should be the maximum value along the path, and the start and end are exactly the same. return the number of distinct good paths. A path and its reverse are counted as the same. For example, 0 to 1 is considered the same as 1 to 0. Wait, hold right there. Hold your horses. Because there is no root? Is that why? Yeah, because it doesn't really matter. And of course, there's no root for this. It's not a, yeah, it's just a tree. You can start from anything. It doesn't really matter. So we have n nodes, and we have n minus 1 edges. The starting node value must be equal to the ending node, and everybody inside must be smaller or equal to. Okay. The pathing is the reverse of the same. So for example, in this one, are these values? There's nodes. So 1, 3, 2, 1, 3. So the path, like, this is a good path. 1. Oh, hold. The nodes by itself. Holy crap, I forgot about that. So additional good path is 1. Yes, 1, 0, 2, 4. This is 3, 1, 2, 3. And the reverse is the same. Oof, the reverse is the same. But they have indices, so I guess it's okay, right? We will be able to check. Note that 0, 2, 3 is not a good path. Yeah, of course, because this one's larger. This one, again, we have values. So 1 and 1 is the same, but there's nothing in between. There's no path in between. 2 and 2 is the same, but there's nothing in between. And that's it. That's just 1, 2, 3, 4, 5. This is 5. I'm very wrong. It's supposed to be 7. Oh, wait, what? 0. Oh, damn. It could be nothing. Good test case. That could be empty. All nodes between. Yeah, you can have no nodes. So, yeah, so 5, 6, and 7. That's just 1. Okay. So, of course, we need to find all the nodes out there have the same value. Ooh. I have more than 2 nodes that have the same value. What's the length? Damn it. 10 to the 5th. I can start from any node. Well, of course, we start from a node that have at least another non-nodes of the same value, right? Otherwise, there's no point. If it's just by itself, then there's no point. So we start from a node that we know has at least another node that have the same value. So we start from the traverse, right? We can do DFS. Yeah, it's most likely DFS, the traverse. And as we traverse, yeah, the thing is, when you traverse, you might go through another path that satisfies. Then you will be repeating, right? You will do the repeated thing. Yeah, this method works, but like just traverse DFS, or go through all the paths and just try to see. But if you do that, you will go through all the paths. Wait, you go through all the paths? Yes, you go through all the paths. So I think with 10 to the 5th, you can only do ON. O(n) log n. It's the most you can do. So through one traversal, we have to hit all possibilities, which means it doesn't really matter from where we start, right? It just means from this one we start, and oh wait, it does matter. Like if I start from 1, it will never realize it's 3 and 3. Damn. Ooh. From any node, and I start going out, right? So the paths, I have all these paths starting from here, right? I have all the paths. Then these paths can be analyzed by itself. Right? I can say I can do this path, I can do this path, but then this path cannot be analyzed. This path cannot be analyzed. Holy crap. Well, maybe another thought. What's the value look like? Now the length is 10 to the 4th. Value is 10 to the 5th. There's one piece of information I never use. I have exactly n-1 edges. So this one help. How does this one help? I don't know how this one helps. it definitely helps. Does it hint? If I have 3 nodes, right, 3 nodes, I only have 2 edges. So that's the only way to connect. At 2 nodes, 1 edge. 3 nodes, 2 edges. 4 nodes, we have 3 edges. So the 4th node can be here, right? Or here. You're going to have 2 orientations for 4 nodes. 5. 5 is this. I can put this, put here is the same. And we can extend. Or 5. And no circles, right? No cycles. No cycles. If we do here, that's exactly the same as this one. So I cannot extend. But what I can do here. That's 5. Because I extend, that will be the same. So 5 I have 3 possibilities. Man, this is never ending. Yeah, this is not working. But it gotta be I feel like it gotta mean something, right? Yeah, it could be a star. It could be a star. Like literally, it could be a star. Then we can have multiple stars. Damn, man. Oh. Now I think it's gonna time out. Like you traverse the entire thing. Yeah, it's not gonna work. But it's connected, which means from wherever I start, I'll end. So from wherever I start, if I DFS this thing, I'll end at any, like all nodes. So I'll know if I can get connected. So any 2 nodes are connected. Yeah, I don't know what I'm thinking. Any 2 nodes, all of these nodes are connected. The question is whether the path, right? And they should only have exactly 1 path. I don't think they will have multiple paths to reach 2 nodes. Two paths. If I have 2 paths to reach, then they have a cycle, right? So because there's no cycle, so each path is unique. So for any pair, we can find a path to connect them. So now the question is, are the nodes inside this path have smaller values than the outside? Okay, if I have the largest value, then it definitely exists a path, right? Because 3 is the largest, so it definitely exists. Here, 2 must exist, right? But we don't know if 1 exists. So I can consider, let's say, consider 3. Once I consider 3, then I can remove the 3's. Okay. So let's say all the pairs have the largest value. They all work. They all work, right? So we get that. And then we remove these nodes, right? If we remove these nodes, we remove the largest value nodes. How do we remove these nodes if they're in? Holy crap. Yes, that's the way, right? You find the largest node, you get all the possibilities, and you remove them. Remove the nodes with the largest value. And when you remove, are you really removing them? How? Like if this one connected to all of those, oh, you just remove this value from the edges, right? You remove them. Now once you remove, this might no longer be a tree, mind you, right? It might no longer be a tree. Oh, how do we remove? So initially everybody belongs to the tree, and then the largest value I want to remove them. In this case, this node's connecting to it's only connecting to 1. It's on the outside, so if we remove it, it doesn't hurt. This one doesn't hurt as well. Now I want to have 2, which is only by itself. So this one doesn't have anything except for itself. So we don't have additional ones. So I want to remove this. And when I remove this and remove this node has no connection and this node has no connection. So they no longer can be connected. How do we know they are no longer connected? You can't just run. No, you cannot just run a DFS just to see if the 2 are connected. Because when you remove, I say you remove this, okay, this node, you remove this one, remove all connection to the rest. Then how do you know if this can still connect? This one is the same. We start from 3, remove it, doesn't hurt. 2, how do you know they're still connected? I would say this, remove it connected, so we do 2. Then we remove this and remove this. And then 1 is still connected. Yeah, that's the thing. How do you tell, or maybe we can cheat a little bit. In graph, determine whether two nodes are connected. It's gotta be a fast algorithm to do this, right? How? Yeah, that's, you have to do it so many times. I don't think it's, plus once you remove, and what if you have multiple, more than two, then you have to determine which pair is reachable. Holy crap. I mean, maybe we can BFS it. I don't know. It's kind of, this one has an idea, well, it's interesting, but I don't know how I can implement this. Or if we break it open, if I can have the remaining tree, like I know how the tree breaks up. I mean, think about it. Think about it. If you are the edge, when you break off, there's no hurt. But if you're not the edge, which means you connect to somebody else, no matter how you connect, when you break up, then there are part of the things are not accessible. So you break up with this, right? Then this is by itself, but it might still be connected from another way. Wait, hold on. And then this one connected to a tree, this one connected to a tree. If I break this and then break this, like if I break these, this subtree and this subtree will no longer be connected, because if they are connected, then we have a cycle, right? So whenever we have something, some nodes, and then we break it, then inevitably, right, no matter how many it's get connected, if I break it, then we will result in multiple subtrees. Okay, there'll be multiple subtrees. Can we represent what this subtree is? Can we? So in this case, right, this connects to this. So its subtree starts, this is the root of the subtree of this, right? And then it is sure that this has no connection to everybody else. So once I cut this tie, and its ties does not go back to connecting any of these things, right? So when I cut this tie, then this becomes the root of its tree. So we go to this node, right? We go to this node, and this will be the root. So if I want to cut this, I temporarily treat this one as a root, and all of its children become roots, because they just cut ties with this. They cut ties with this, and that's it. That's all that it affects. Now we have these like bunch of subtree, and then within each subtree, I continue remove. Hold on. So I have this value. I have these nodes. And for this node, I want to sever the ties. So I just sever it. Okay? If I sever, then you'll be in separate. Hold on. So first one, I sever, and then we have this, and then this one will sever. A subtree. Every time we sever, we're sure we create a new subtree. We just go to that subtree. We just just keep branching out. Okay, I have an idea. So the idea is for each tree, right, will have its edges. Ooh. No, I don't think this works because you don't know which edges belong to what subtree. You don't know that. You don't know that. All you know is at the beginning level, right? We know, let's say, node 1 connects to the, yeah, if this is the case, it's fine. We can just sever it. We can remove all the nodes that has value of 3 and no breakout. So the next level, it's still this tree. Then we go to node 2, and 2 we point into 0, and the 3 is already gone, and 2 pointed to 4. So for the 2, I don't know, point into node 3 and node 0, node 3 and node 0. So this is what the 2 currently looks like. So we go to 2, we see this, and so we have the remove 2. So 2 pointed to 0, so I say, okay, I sever that. Then we go to 0, or remove 2, and 0 becomes its root. So that's a separate thing, which is just 0 to 1, and 1. And all the things that 1 connects to. Oh, of course, in this case, the 0 doesn't have. Because when we sever, I say this is the root of the tree. So all the nodes that it connects to at the moment, they form the subtree. Yes, then it works. We find the largest of the current tree, trim it, right? We trim it, and after we trim it, if it doesn't produce a subtree, if it doesn't break into 2 subtrees, then we keep trim until we trim it. They will produce like if it's this node, if we trim it, it will produce multiple subtrees, right? So like if it's only one kid, then that's fine. If it's two, you have two, then when you sever it, you will have subtrees. Then we get a subtree, we create a new, what is it called? Matrix? Graph? What's it called? Adjacency matrix, right? So we create a new adjacency matrix for this subtree, and then we recurse. And when we recurse, we pass in the current node that needs to be removed. And we simply just look for it, right? We have all the nodes, and then we, get the values. Get the values. Get the values. Because this will hit its children, and its children need to hit its children. Oh. Now, the adjacency list will not be that easy to make, because I have to go through every single one. Yeah, if I have this, I need to go make this, put it in, get this one, put it in, and everyone has their children, and their children has to be put in as well. But a good thing is, I don't think the tree will have like too many childrens. Everyone, like 2 or 3. I mean, like it's either not deep, or if it's deep, then everyone has very few. So we just reconnect. So we delete. So maybe O and login this solution. We'll try it tomorrow. Maybe it works. Maybe it doesn't. We'll see. All right. Anyway, I'll see you guys tomorrow. Adios.